This provincial city hosts the headquarters of Shima Seiki.
Mr. Shima, it's a
nice to meet you.
pleasure to meet you, sir.
Masahiro Shima is the company president. He's known for spearheading a revolution in the industry of knitting machines. He finds inspiration in objects of beauty and fine engineering. Adorning the lobby of Shima Seiki's headquarters are two Ferraris. The legendary cars are a reflection of Shima's philosophy.
Buddy,
Look at the gorgeous color of this Ferrari. Our company develops machines and systems for the knitting industry. It's always about combining sensitivity and technology. The beauty of Ferrari's design is inspiring in this regard.
Shima founded his company at the age of 24, and for more than 50 years that followed, he has remained at the forefront of innovation.
Oh, look at all these machines.
The company's headquarters also harbors the factory. All of Shima Seiki's knitting machines are made here. Every year, nearly 9,000 units are shipped to more than 90 countries. The company employs 1,200 people. It boasts annual sales of more than $400 million. Shima Seiki's catalog offers an array of 12 types of knitting machines. This compact model produces gloves. This 90-inch model can knit large swaths of knitted fabric. From complex shapes and designs to intricate patterns and stitching, these machines are engineered to meet the specific needs of the garment industry. Shima Seiki's flagship product that brings together all of the company's leading technologies is the Mach 2X. This fully automated knitting machine produces ready-to-wear garments in a single cycle. The Mach 2X hit the market in 2008 and since continues to be improved. At $120,000, it's twice the price of a standard machine, but it's in a class of its own. From garment design to finish, the Mach 2X's system is computer controlled. There is no other knitting machine like it on the market. To learn more about what this technological marvel can do, we visit Shima Seiki's Garment Design Center. Before the Mach 2X comes into play, a design for the garment has to be created. This can easily be done with Shima Seiki's designing system. Fashion designers can create and modify their models using a proprietary software interface called the Apex 3. Here's how the system works. Normally, a paper pattern of the garment would have to be prepared. In Shima Seiki's design system, the pattern is created virtually and can be visualized in 3D. This example shows how to make a dress. Designers can select a yarn from a database of 174 different types. Here, a green-colored cotton thread is chosen. Then, a stitch pattern is selected from a variety of 1,557. The effect is rendered with stunning accuracy. A cable pattern is picked and applied to the virtual dress. The pattern can then be adjusted freely and quickly. The designer's creation can now be examined in full 3D. When the parameters are set, the data is saved onto a USB flash drive and transferred to the Mach 2X. The machine is then activated. The knitting machine begins churning out an exact replica of the newly designed dress. The entire process from computer sketch to completed garment took only 37 minutes.
Voila! It's wonderful. Oh, and look at the detail. That is absolutely beautiful stitching. That's gorgeous.
No seam.
No seam at all. That is wonderful. And on the inside, where the seam would normally appear?
The Mach IIX's entirely automated and seamless technology can produce unparalleled knitwear. This dress features an elegant flared hemline. A similar dress, such as this gray one, was made using a conventional knitting machine. Flat pieces of knitted textile were first produced. Then 16 different panels were cut and sewn together by hand to create the flare. The dress made on the Mach IIX, however, is completely seamless. The flare is knitted into the structure of the dress, giving it an elegant and flowing line. A seamless garment is lighter and more comfortable to wear. It's also stretchy and naturally hugs the body. The Mach IIX is revolutionizing the knitwear industry, changing the way garments are designed and produced.
To understand how a knitting machine works, we first need to know how basic hand knitting is done.
Hand knitting is usually performed by manipulating two needles to create a series of stitches. A row of stitches is made by transferring successive loops of yarn from one needle to the other. A closer look in slow motion reveals that first, the right needle is driven through the stitch at the tip of the left needle. It then catches the yarn and pulls it back through the stitch. The new loop is transferred to the right needle, creating a new stitch. Once a row of stitches is completed, the process is repeated in the opposite direction, adding row upon row of stitches to the fabric. A close-up of the fabric shows how the loops are intertwined, forming a regular pattern. Now let's compare this with mechanized knitting. In a basic knitting machine, hundreds of needles are laid side by side on two flat metal beds. A carriage moves back and forth across the needle beds, drawing the yarn to the needles. The carriage not only draws the yarn, it also activates the needles. Let's see how this works underneath the carriage. The yarn is laid across the leading edge of the needles. The carriage activates the needles in succession, creating a new row of stitches. Rows of stitches are formed as the carriage moves back and forth. Human hands can manipulate only 2 needles at a time. Machines can activate hundreds of needles, constructing fabric much faster than any human can.
For a garment such as a sweater, knitting in a straight line just won't do. The edge along the neckline, or where the sleeve meets the body panels, for instance, must be shaped along a curving line. Let's see how this is done.
One way of giving shape to a knitted fabric is to successively reduce the number of stitches in each row. First, the needles progress as usual through the row of stitches, until there are only 2 loops left before the edge of the fabric. Here, the needle catches the last 2 loops at once. The result is a row that has been shortened by 1 stitch. Reducing the number of stitches row by row creates this type of shape. Now let's see how this is performed on a knitting machine. This graphic shows 2 needle beds facing each other. To decrease the row by 1 stitch, the needle in one of the beds transfers the yarn to its counterpart. The bed moves sideways by 1 notch, and the loop is transferred back, putting two loops on top of each other. The machine's two needle beds are set at an angle in an inverted V shape. This allows the needles to move back and forth and transfer the yarn from one needle bed to the other. Here's a close-up of a double needle bed in action. The needle on the top bed moves forward, allowing the opposite needle to rise, catch the yarn, and pull it back through the lower loop. Then the top bed slides over by one notch, and the action is repeated. The transfer of the loop makes it possible to decrease the number of stitches and to create all kinds of shapes.
Before the arrival of Shima Seiki's whole garment knitting machines, the different parts of the garment had to be cut out from a flat fabric using a paper pattern, then sewn together by hand. Shima Seiki machines are able to produce the whole garment in one three-dimensional piece, doing away altogether with the cutting and the sewing. So how did Masahiro Shima develop this technology? Well, it all started with a glove.
As a young boy, Masahiro Shima was very fond of inventions. He first encountered a knitting machine when he took up a part-time job at a repair shop. The device he was assigned to fix was a glove knitting machine. Knitted gloves known as gunte in Japan were widely used for manual work. At $2.20 a dozen back then, they were considered a very expensive item. The knitting machine was manually operated. Weights were used to tug on the fabric from below to keep it from springing back, causing the yarn to tangle and jamming the machine. When a glove was completed, the weights had to be removed, the machine had to be set again, and the weights put back on. This was a time-consuming process, and one of the reasons why gloves were so expensive to make.
I thought glove knitting machines were clunky, so I dreamt of making one that could work a little faster and produce better results.
In his attempt to improve the machine, Shima focused his attention on one component of the needle beds: the metal partitions between the needles. Shima extended these partitions and gave them an active role by making them movable. Here's how he imagined they would work. After a needle pulls the yarn through the loop, making a stitch, the partition next to it presses down on the newly made stitch. These moving partitions are called sinkers. Stitch after stitch, the fabric is pressed down through the gap in between the needle beds. This system eliminated the need for weights, making the whole process of glove knitting a lot more efficient. At the age of 24, Shima set up his own company and proceeded to further develop his technology. In 1964, he produced the world's first fully automated glove knitting machine. At the simple push of a button, the device kicked into action and produced a glove in just 2 minutes and 15 seconds. Soon after the successful launch of his machine, Shima had an epiphany that would have profound consequences on the fashion industry.
If you narrow the wrist and reverse it, you have a turtleneck. Now, imagine the thumb as one sleeve and the pinky as another sleeve. And then knit the middle fingers together, and you have a sweater.
The fingers and body of a glove are knitted in a seamless cylindrical shape. Making this three-dimensional shape requires two needle beds laid opposite each other in an inverted V shape. As the carriage moves in one direction, it activates the needles on one bed, and as it moves in the other direction, it activates the needles on the opposite bed, creating a spiraling row of stitches. Here's the same animation in two colors to highlight the stitches made by each needle bed. Once the yarn reaches the edge of the glove, it reverses its course and makes another row of stitches on the opposite side. When the carriage reaches the edge, it activates the needle on the opposite bed, which transfers the yarn across. Shima's glove knitting machine could knit all the different parts of a glove seamlessly with only one yarn. Unlike gloves, however, other garments involve a much higher degree of complexity. The machine would have to be able to make different shapes and patterns as well. Shima knew that developing such a machine would take several years.
Developing a machine that could knit a whole garment was simply too difficult and would take time. So I decided to start by making a device that could knit specific shapes.
Shima began by developing a knitting machine that could shape flat fabric to produce collars. He also developed ways of producing different kinds of patterns and motifs. The 1980s saw another major development, advances in computer technology, which brought the performance of knitting machines to a whole new level. From his first experiments on the glove knitting machine, it took Shima 30 years before he could start developing a machine that could produce a whole garment seamlessly. One major obstacle, though, stood in the way. The inverted V-shaped double needle bed had serious limitations. To produce seamless stitching, the needles on both beds have to work in tandem. To make shapes and patterns requires the needles and beds to interact in different fashions. For seamless stitching, all the needles on both beds are active at the same time, whereas for shaping, the needles on one of the beds need to be free to allow for the transfer of the stitch. How did Shima reconcile these two apparently incompatible objectives? Seamless tubular stitching is realized by skipping every other needle. In this configuration, shape stitching, or putting two loops together to narrow the fabric by one stitch, requires the yarn to be carried 2 needles over. The solution for Shima was to pair the needles, giving each needle different roles. The machine could now stitch seamlessly and shape all at the same time. In September 1995, the world's first commercially produced, fully computerized whole garment knitting machine was born, the SWGV. The following month, Shima proudly demonstrated his new invention at the International Textile Machinery Association exhibition in Milan. For the first time, people witnessed a knitting machine producing an entire garment, shaped, seamless, and ready to wear.
Our model, when standing idle, looked like any other standard V-shaped needle bed that people knew well. But when the machine sprung into action, everyone, including our competitors, was bewildered by how it worked. They just couldn't figure it out. People called it Oriental magic.
Oriental magic, eh? Well, it sure seemed like magic. Though industry reps were wowed by the SWGV's ability to produce a seamless whole garment, they still didn't buy it. The machine had a major flaw. It was limited to making coarse stitches and couldn't produce fine knitwear.
To make fine knitted fabric, the yarn has to be thinner and the stitches smaller. For this, more needles are needed. This determines the gauge. A 7 gauge means there are 7 needles per inch. The higher the gauge number, the finer the stitches. The SWGV technically had a 14 gauge, but it can only produce 7 gauge knitted fabric. The main reason, as explained earlier, was that it only used every other needle for stitching.
So Shima went to work on developing the technology even further, and thus began a real revolution in the garment industry.
This This sweater was made using Shima Seiki's 7-gauge SWGV knitting machine. Luxury brands require a much finer level of detail than a mere 7 stitches per inch. The only way of raising the gauge on the SWGV was to add more needles on the beds. But Shima had another solution in mind. Instead of squeezing in more needles, he would add 2 more beds to the assembly, effectively doubling the total number of needles. Adding extra needle beds was the most revolutionary idea in more than a century of engineering history. Once again, Shima figured out the riddle, but he had to overcome a major obstacle: the needle itself. This latch needle was the industry standard. It had been invented in Britain in 1849. The latch is attached to the body of the needle at the base of the hook and swings back and forth along the axis. This enlarged scale model shows how it works. The latch's role is to enable the needle to pull the yarn through a loop without snagging. As the needle extends outward, the loop it supports pushes open the latch. When the hook has caught the yarn, the needle retracts and the loop pushes the latch closed, allowing the needle to effectively pull the yarn through the loop to make a stitch. This latch needle wouldn't work in a 4-needle bed configuration. The needle beds need to be kept close together for fine, tight stitching. A wider gap between the beds would result in loose stitches. With the beds so close to each other, the latch on the needles of the lower beds could not fully open. Also of concern was the length of the needle stroke. The overextension of the needle would reduce the machine's knitting speed and efficiency. So the latch needed to go, and the needle had to be reinvented. Shima set himself to work on designing a needle that didn't require a latch. He worked closely with his top engineer. Reiji Arikita had to develop a needle based on Shima's specifications.
Here are the documents we used for the development. They were drawn during meetings with President Shima. He kept drawing sketch after sketch. Based on those outlines, we devised prototypes and tested them. But things didn't go very well. The type of needle Mr. Shima had in mind wasn't right for knitting.
Over the next year, Arikita kept making and testing prototypes based on Shima's ideas. Nothing worked. This put a strain on the engineering team.
The R&D team told me it was impossible. People in the engineering department said they were getting fed up. But we didn't give up, and in the end our passion overcame our frustrations and led us to a breakthrough.
The design that put an end to this conundrum was called the slide needle. This needle is made of 2 separate parts. The outer part bears the hook, and the slider replaces the latch. Shima had once again proven his genius. The concept was at once simple and clever. This needle's biggest advantage is that its reach is 1/3 shorter than that of the latch needle. Another cool feature is the slider's pronged tip that allows the hook to retract and pull the yarn through the loop without snagging. The gap also lets the hook of the opposite needle reach inside the slider and catch the loop. This animation shows a bed of latch needles at work. And here's a bed of slide needles doing their job. They transfer the yarn in half the stroke of the latch needle. It was the first time in 150 years that the knitting needle had been improved. And it provided a solution to the 4-needle bed configuration Shima had in mind.
The bed on the lower left and the one on the upper right transfer the loops to each other, knitting the front of the garment. The beds on the lower right and on the upper left do the same for the back of the garment.
With the number of needles now doubled, Shima Seiki could develop an 18-gauge knitting machine that could also knit more intricate shapes and patterns. In 1999, the company launched a new knitting machine that featured 4 needle beds, the SWG-X. 9 years later, in 2008, a new upgraded model was released. Its carriage was smaller and moved faster, cutting knitting time by 20%. This efficient, high-speed, and fully automated knitting machine was the Mach 2X.
The first whole garment machines could only produce flat sweaters. The Mach 2X, on the other hand, is able to seamlessly knit elegant three-dimensional one-piece dresses. Look at the silhouette of this dress. The line follows the body as if it had been designed on a paper pattern. Whole garment knitting creates volume for the bust and the flare effect you see down here.
Another marvel of technological development from Shima Seiki is the company's state-of-the-art design interface called Apex 3. The software is specifically engineered for the apparel industry. It can handle just about any degree of complexity in the structure of a garment. From designing to output, it interacts seamlessly with the knitting machine, making it a powerful creative tool for the fashion designer. The system makes it possible to design garments in a virtual environment while simultaneously programming the knitting data. Here's the example of a dress starting with the design layout. And here's the programming interface. The programmed data for every single stitch is color-coded and can be visually confirmed. Let's see how the interface works. Here's the knitted fabric before a specific pattern is chosen. Each stitch is displayed on the right side of the screen. The color-coded toolbar at the top of the screen provides a list of available stitches. In this example, the blue and purple tool icons are chosen to create a cable pattern. As the color codes are laid out in the programming interface, they're immediately rendered on the left of the screen, showing what the fabric will look like. The use of color codes makes it much easier to program an intricate design. The innovative garments produced by Shima Seiki knitting machines owe as much to the advanced design interface of the Apex 3 as they do to the machines themselves.
My sales pitch to our customers is that if you buy Shima Seiki knitting machines, you will be able to create designs that machines made by other companies cannot. Drawing out the full potential of the machine depends on the designing and programming power of the Apex 3.
Since the introduction of the upgraded whole garment machines, Shima Seiki sold more than 2,000 units in Japan and 5,400 units to countries internationally, mostly to Italy. Some of the world's biggest fashion brand names concentrate there. When Italy's apparel industry suffered a major downturn in the 1980s, as manufacturers moved their production lines to developing countries, it was Shima Seiki that came to the rescue.
Northern Italy is a major hub of the textile industry. The town of Carpi is Italy's main manufacturing center of knitwear. About 1,000 related businesses are located here. We visit a local factory that operates as a subcontractor for major Italian clothing brands. It produces about 60,000 garments every month. On the floor are 90 whole garment knitting machines. Whole Whole garment machines like these are not unique to this company. There are about 2,000 of them in factories in and around Carpi. The first of these models were shipped to this region about 15 years ago. At the time, Carpi's knitting industry was divided into smaller specialties, such as knitting, cutting, sewing, and finishing. Most businesses had started off as family enterprises operating out of people's homes. Since the mid-1980s, the industry had been facing a serious crisis. Companies were moving their manufacturing operations abroad. Textiles and fabrics could be produced at a fraction of the cost in developing countries. Some companies resisted the trend and instead invested in more advanced technology. This factory first introduced Shima Seiki whole garment knitting machines in 1999. Now it operates 100 units. Christian Tabaroni is sales manager at the company. Adorning a wall in the factory is a picture of him with Masahiro Shima.
It goes without saying, but these machines are simply the best in the world. There's nothing better out there.
Tabaroni says it was the closure of a sewing factory that prompted him to introduce Shima Seiki machines.
When I started investing, I strongly believed in innovation. The most important thing in life, if you want to have a future, is to keep innovating. And Shima Seiki is the leading edge of this technology.
Now, the factory's 100 knitting machines are operated by only 5 technicians. Whole garment technology has eliminated the need for cutting and sewing, allowing the company to compete against cheap imports with made-in-Italy products. The company's sales have tripled since it started using these machines. Tabaroni invites us to see some of his factory's masterpieces.
For example, this is Calvin Klein. It's original, eh? It's not fake. Questo è Versace.
Tabaroni started taking orders from luxury brands after he acquired Mach 2X knitting machines. He even took things one step further and created an entire collection under his own brand name. He's proud to show off the company's signboard.
World leader of whole garment production.
Still in northern Italy, we head for another factory, this time in the town of Avio. Last year, this brand ordered 60 Mach 2X machines, all at once. Its main products are 100% cashmere sweaters. The designing of the sweaters is done right at the factory. Programmers use Shima Seiki's Apex 3 designing interface to fashion the brand's newest collections based on models drawn by the designers. Once the programming is complete, the data is taken next door and transferred to a Mach 2X, which will then produce a sample. The design room is full of samples of garments that will soon be put on the market. The designers and the programmers work together to make finer adjustments.
Could you narrow the pocket from 16 to 14 centimeters?
Okay, I will raise the edge by 2 centimeters and reprogram the output immediately.
The changes are instantly implemented. Once the sample is finalized, the Mach 2X's spring into action to mass produce the new item.
The designing system allows us to save time and money on the development of new products. Another advantage of the whole garment knitting machine is that it doesn't require any manual intervention, so we can produce affordable products made with quality materials. We wish we could acquire more machines, but right now the price is a bit too high.
And now, even luxury brands such as Max Mara are introducing whole garment knitting machines into their factories. Max Mara is known for having broken new ground in the field of the pret-à-porter, an industry that brings together the concepts of tailor-made garments and mass production. The brand is hoping to leverage the potential of whole garment knitting to create a